This will be a review of exit slip 13, where we were asked to solve an application of rational equations. It's another one of these distance, rate, and time problems. So just to refresh us briefly, we know that distance is equal to rate times time. You could plug in some values and make some sense of that, which in turn implies that we could express rate as distance over time, or we could express time as distance over rate. So these are three different ways to express the relationship between those three quantities. When doing application problems, a lot of times we need to spend a fair amount of time reading the problem, interpreting what we know, what we don't know. And one of the ways I like to do that with problems of this sort is to build a little bit of a chart, I guess. It just helps me feel organized. So I'm going to use that same technique here in case it's helping you also. So I know this problem is going to be about distance, rate, and time, so I just like to have space in my chart for those three quantities, distance, rate, and time. So let's go ahead and read through it, and then we'll fill in as much as we can. So in this problem, we're told Kellen's boat travels 12 miles per hour. So that's a value that we're given, 12 miles per hour. Our job is to find the rate of the current. So it sounds like the unknown quantity is the rate of the current of the river if she can travel 6 miles upstream. Okay, so 6 miles upstream is another number we're given. In the same amount of time, that's important. So let's see, let's underline that. In the same amount of time, okay. So whatever time we have up will be the same as the time down, okay. If she can travel 6 miles upstream in the same amount of time she can travel 10 miles downstream. All right. So again, I'm reading through it. I'm underlining a little bit. You can do whatever helps you the most to digest the information in kind of an organized way. So with boat problems, typically the rows of our chart will be concerned about the downstream and the upstream. So in this case, upstream is mentioned first, so I'll put upstream first, and then I'll put downstream. If it were like a plane problem, you may instead have like with the wind or against the wind, or if it's a car problem, you may have, going one direction and then the other. So it's common to see this type of problem with cars, planes, boats, things that move. So let's see what we can fill in for sure. I'm going to go ahead and fill in the 6 miles upstream. That's a distance, right? 6 miles is a distance. And specifically, it's a distance up. So 12 miles up would be the distance we're told for upstream. Similarly, 10 miles is a distance, and that's downstream. So even just conceptually, it makes sense to me that the distance traveled down, um, uh, oh, sorry, I don't know why I somehow put 12 instead of 6. What I was about to say made no sense. I was like, what went wrong? So sorry about that. I had somehow changed this 6 into 12. Debating if I should restart all over, but hopefully that wasn't too much of a stumble. You can yell at me later if it was. So I was just going to say that conceptually it should make sense that if the time is the same, we should go a further distance downstream than upstream, right? Because we go faster when we're going downstream. So hopefully that helps a little bit. So I've used my 6 miles up, I've used my 10 miles down. I understand that whatever time expression I have here, it can be set equal to the time expression here. So that's going to be how I build my equation. So what we still need some help with is the rate. Now, in this particular problem, we know that the boat itself goes 12 miles per hour. So I can incorporate that 12 into the rate for both up and down. But what I don't know is the rate of the current. So we could let X be the rate of the current, or maybe just to do a little different this time, I'm going to let C be the rate of the current. I'll use C for current, might as well. And now we just have to make sure we understand how the current impacts the rate in each direction. So I'm going to talk about down first. If I'm going downstream, the current is going to make me go faster. So I'm adding the rate of the current. If I'm going upstream, then I'm going against the current. I'm going to be slowed down by the current. So the rate for this problem involves not only the boat speed, but also the current speed, since the current is acting on the boat. So hopefully that seems pretty decent so far. The last thing to do then is to come back up to our relationships up top here and ask ourselves which one of these scenarios is solved for time, and that would definitely be this piece here. So since we have symbolic representations for distance and rate, I'm just going to fill in my time block by saying that time is distance. So in the upstream case, it's distance of 6 divided by rate of 12 minus c. And for downstream, it's going to be that distance, 10, divided by the rate down, which is 12 plus c. Now, those two quantities can be set equal to one another because the time up and the time down are the same. I don't even really care about how much time it was. I just need that relationship that they're equal to build an equation. So I'm going to go ahead and set the time up, which was 6 over 12 minus c, equal to 10 over 12 plus c. And again, with this type of equation, personally, I'm a big fan of cross multiplying. So if I cross multiply, I will get 6 times 12 plus c, and I'll set that equal to 10 times 12 minus c. So that would be the cross multiplication step. From there, if you want to divide by a common factor first, you can, but most people, I think, at this point just begin distributing. So I'll go ahead and do the same. So 6 times 12, I think that's 72. 6 times c is 6c. On the right side, 10 times 12 is 120. 10 times negative c is negative 10c. So at this point, do your algebra dance in whatever way you see fit. I'm going to go ahead and move all my c's to one side. We'll do this in a couple steps here. So I'm going to get 72 plus 16c is equal to 120. So then I'll move all my numbers to the right side of the equation. So I'll get 16c is equal to, let's see, and what's that make, 48. And then we'll divide by 16 to get c alone. So it looks to me like we're finding that c equals 3. Anytime we're in an application problem, it's a good idea to interpret your solution. So I'd rather not see us just box it off here and walk away because c has a unit. It has a unit of measure because it means something in this context. So c is the rate of the current. I could have even been a little bit more specific and made sure we're clear. It's in miles per hour. So rate in this problem, like we're familiar with rates for driving, we typically use miles per hour. So, oops. I will just go back and state my final solution is the rate of the current is 3 miles per hour. Cool. And now, of course, if we wanted to, we could even find, how much time did it take to go up, which will be the same as the time down, all those kind of things. But I'm just going to go ahead and end at answering the question we are asked for, which is the rate of the current. So I hope you enjoyed this application of rationals. It's a pretty practical application.